How's it going, guys? It's Chris here, and this video covers the AS topic of finite state machines. Traffic lights are an example of an FSM. By the end of the video, you should be able to understand why. Here's the agenda. We'll start with defining the term finite state machine and looking at their key characteristics. Then we'll move on to look at two ways finite state machines can be represented. So, a finite state machine is a computing machine that has a fixed set of possible states, a set of inputs, and a set of possible outputs. The phrase fixed set of possible states is just another way to say finite states. And finite is a key word because whenever we implement a finite state machine in hardware or software, we only have limited memory space to play with. That's why it's finite. Finite state machines don't actually need to have an output. You'll only see ones that do at A level. You might also see the term finite state automation to describe a finite state machine that has no output. Finite state automata is the plural version. Now, despite me using a picture of an old-fashioned mechanical machine when referring to a finite state machine, we often don't mean a literal physical system, but instead an abstract creation we use to model simple computation and decision making. In this video, we'll look at one physical example and one that's completely abstract, just so you're familiar with both. Just in case you haven't quite understood what a finite state machine is yet, let me just re-emphasize. Really, they're conceptual machines which can take some input, maybe a letter or a number or a physical input, like a user pressing a button. Whatever the input is, it either causes the machine to just remain in its current state or to change the state it's in. For example, you moving a slider on one finite state machine could just keep the machine on like it was already, whereas applying the same input to a different machine might actually turn it off. In this example, the state of the machine is being either on or off. Now, we need to mention a key feature of a finite state machine, which is that the state it changes to is based on both the current state and the input value. To demonstrate this, think about a ballpoint pen, which is a simple example of a finite state machine. When you apply the input, i.e. you pressing the button, the machine changes state so that the pen nib extends. However, when you press the pen's button again, the nib retracts. This demonstrates that, despite the input being the same, the result is different because the current state is taken into account as well. Long story short, applying the same input multiple times doesn't necessarily lead to the same result. This property means the machine's entire history can be summarized in its current state. How it actually got to that state is irrelevant. You can just look at the current state and its input. Now, we have some theory nailed down. Let's look at the first way we can represent FSMs, which is with state transition diagrams. These show the machine's behavior visually, and here's the state transition diagram for the ballpoint pen example we just talked about. A circle represents the state of the machine. As you can see, we have two states in this example, which are the pen either being retracted or extended. We've labeled the states S0 and S1, but we could add a key to connect meaning to them. Arrows represent a transition to a state, and we label them with the input that has triggered this transition. Just like we looked at, when the pen's current state is retracted at S0 and you press the button, the pen transitions to a state where the nib is extended at S1. Before we move on to the next example, here are two other symbols you need to know. The initial state is where the machine starts from and resets to. Naturally, you can only have one initial state. A double circle represents an accepting state. You might also hear it called the goal state, and it's the state which shows whether an input is acceptable. You can have more than one accepting state. Here's a more complicated state transition diagram, but it's not as bad as it looks. It's actually to do with another area of your course, regular expressions. But don't worry if you haven't covered that yet. You don't really need to have done so in order to understand this. All regular expressions can be represented as state transition diagrams. We're going to use A, B, asterisk as our example regular expression here. The asterisk means 0 or more, so this regular expression means you want one A inputted, then followed by as many B's as you want. Despite it being a bit abstract, the point of this FSM is to determine whether the input given is acceptable according to this regular expression. Our possible inputs are only going to be the letters A and B. Right, let's break down this diagram then. As you can see, the state labelled 0 is the initial state, so we can start there. If our first input is A, then you transition to 1, which is the accepting state. If you then inputted B, then you just remained at 1, because the arrow on the diagram loops back on itself. No matter how many B's you add from 1, you just keep transitioning back to that accepting state. Hopefully you can see that this matches our regular expression, and it being at the accepting state is telling us that our input string is okay. However, if you then input an A from 1, or you started off from 0 with a B, then you have a problem, because the machine transitions to 2 instead. No arrows go from 2 to 1, so you're stuck here forever at what is essentially an unaccepting state. You just keep inputting A's or B's from 2 without a change of state. It means our string doesn't match the regular expression. Now, although this example may seem even more boring than the pen one, using these diagrams for regular expressions is actually a really important tool for computer scientists. Let's now look at our second and final way of representing finite state machines, which is with state transition tables. These are like the truth tables you find in logic and show the effect different inputs have on the current state. Here's the one for the pen example. You can see our 3 columns, which are input, current state, and next state. At A level, we also might add an output column if it were applicable. By current state, we mean the state the machine's in before you add the input. And the next state is the one the machine transitions to because of the input. Just so you can see both representations together and see a slightly more complicated state transition table, here's the regular expression state transition diagram from earlier. As you can see, for each possible current state, we test each possible input and show the effect of this in the final column. When constructing these tables, you just need to make sure you are methodical and cover every possible combination. I'd suggest you now pause the video and see if the table makes sense to you according to the diagram and vice versa. And we're done. Let's have a quick recap. We have defined the term finite state machine. This could be a really standard 2-mark question, so learn this definition. A finite state machine is a computing machine that has a fixed set of possible states, a set of inputs that change the state, and a set of possible outputs. Hopefully you now also understand that the next state is based on both the current state of the machine and the input. This should be extra apparent when you look at the 2 different representations, state transition diagrams and state transition tables. Thanks for watching.